Welcome back to Dave Does Math from Home. This is part 2 of our video series on tangent planes. In the first part of this video we talked about the relationship between what we're doing in this section and what we did in Calc 1 with one-dimensional derivatives. So hopefully that was very useful in connecting these two ideas to each other, grounding this in something that you're pretty well aware of. In this video, or in the first video, we also talked about how to get tangent planes for explicit functions. So the functions that we did examples for all looked like z is some function of x and y. Z was isolated, it was by itself. We had x's and y's over here that stuff was happening to. We could very easily take partial derivatives of this thing with respect to x, with respect to y. There is a different kind of function that we need to also learn how to take these tangent planes for. Actually, let me not erase that. We'll leave that here. F of x, y. This is explicit. The other kind of function that we're going to talk about is implicit, and those things look like this. F of x and y and z equals 0. This is how we get an implicit function in 3 dimensions. And this can be useful if you have z's sort of like mixed in with your x's and y's and it's very difficult to extract them. You can go sort of back and forth between these two things. So sometimes if you're given an implicit function, it's not too much work to change it to explicit. You can sort of solve it for z and then it becomes an explicit function and you can do the technique we already learned. If you're given an explicit function, you can always just subtract z from both sides, and now you have 0 equals f of x, y, minus z. And now you have an implicit function, and you can always do, so if you want to just only learn this one technique, and just only ever do it implicitly, you can change these into implicit very easily, and then not have to try to memorize these two different techniques, because the techniques are very similar. So techniques are similar because this is similar. It's easy to transform this into this, and it is easy to connect this technique with what we just did. So let's do some examples of functions that look like this, so you can kind of see what that looks like and how it connects. So let's take something like 2xy plus 3xz plus 4yz equals, minus 37 equals 0. So this is kind of what I meant when I said implicit functions. We have x's and y's, that's what that is. X's and y's and z's all muddled together in one big thing, but it equals 0. So at least this back end is nice. I want the tangent plane at 1, 2, 3. So in the last set of problems we did, the very first step was finding the z value, because we were only given x and y. And based on that x and y value we were given, we had to find a z value because we needed all 3. Here, all 3 are given to us. We have our x and our y and our z. If you want to verify that this is in fact a plane on this surface, you could plug in 1 and 2 and 3 and verify that when you add it all together, you do in fact get 0. You don't have to do that though. You could skip that. And I will skip that. Instead, because I already have the entire point, I'm just going to go straight into finding derivatives. Only this time I need 3 derivatives. Because this is implicit and I have x's and y's and z's all muddled together all over the place, I need derivatives with respect to x and with respect to y and with respect to z. I need all 3 of those. So the partial with respect to x should be 2y plus 3z. That term is constant, it goes to 0, that goes to 0. So this is the partial with respect to x. And when you evaluate it at 1, 2, 3, we should get 4 plus 9 is 13. And I need a partial derivative with respect to y. And that should be 2x, 0 on this term, 4z, 0 on this term. So 2x plus 4z is my partial with respect to y. And when I evaluate this one at 1, 2, 3, I will get a slope of 2 plus 10 is 12. I should mark this. This is mx. This is my. And now I need a third one. The partial with respect to z should be 0 plus 3x plus 4y. And I evaluate that at 1, 2, 3, and I get 3 plus 8 is 11. This is mz. So now I have 3 slopes. With my 3 slopes, I'm going to set up something that looks almost exactly like this. Well, a little bit like this, in that there will be x's and y's and z's together, but it's going to be linear, and it's going to equal 0 on the back end. So instead of doing like a z minus z1 equals your x slopes times your x terms plus your y slopes times your y terms, we're just going to put all of those slopes together. We're going to have x slopes times x terms. We're going to have y slopes times y terms. We're going to have z slopes times z terms. And when we add it all together, we need to get 0. Hopefully that is readable and not too... I feel like this marker is dying out of me. Z slopes times z terms is 0. Is the end of that. It looks fairly readable. Okay. So this is the version of this that you get when you're doing this implicitly. So we can plug all these things in. This will be 13 times x minus 1 plus 12 times y minus 2 plus 11 times z minus 3, and that will equal 0. And then you can simplify this a little bit. 13x minus 13 plus 12y minus 24 plus 11z minus 33 equals 0. So when you're done, you still want to leave everything on one side. It's important that this thing equals 0, because that's the format for these implicit three-dimensional functions. They always got to look like f of x, y, z equals 0. So we're not going to mess with this side of the equation. But we can combine these like terms, the 33, the 24, the 13. So we can get 13x plus 12y plus 11z minus 33 and 13 should give you 46. Minus 24 should give you 70. No, that's not a z. Minus 70 equals 0. So this is the 3D implicit version of what's going on here. I want to talk very briefly about the relationship between this implicit formula that we have here and the explicit formula we were working with before. So I mentioned earlier that if you have an explicit formula, z equals f of x, y, you can transform that into, this is explicit, you can transform that into an implicit thing by subtracting z from both sides. And then it becomes f of x, y minus z equals 0. And now you're in implicit mode. And the tangent plane for an explicit thing is z minus z1 equals mx x minus x1 plus my y minus y1. And hopefully we can see that already most of this matches. Let me do that in a different color. And bigger. Z minus z1 equals mx x minus x1 plus my y minus y1. This is the explicit version of this tangent plane. And this part of it matches. So the only big difference here is that this thing is z minus z1 on the other side of the equation, and this has a slope times z minus z1 over here. So I want to ask what happens if we decide to subtract this whole thing from both sides of the equation. If we do that, we'll get 0 over here, and it will equal mx x minus x1, still matches here, my y minus y1, still matches here. We'll get negative 1 times z minus z1, which almost matches here. The z minus z1 matches. We have a defined negative 1 instead of this mz. But that checks out because if you're doing this implicit thing, the derivative with respect to z of this is always going to be negative 1. So that's why when you try to transform this thing into this thing, you're getting a negative 1 here. So these two different equations really are essentially the exact same equation. If you want to do all of your homework problems by transforming, the ones that start implicit, you can do those with this implicit formula here. If you want to do all of the explicit ones with the same implicit formula, you can do that by just very easily transforming them into implicit things and just having a negative 1 here on your z's. You might have to do some rearranging on the end to get it back into a format that my math lab wants. But it's very possible to do. It's just very simple algebra to do those rearranging steps. Or if you want to memorize this as the point slope form for explicit functions, and you want to memorize this separately as the point slope form for implicit functions, that's also fine. You can do this however you like. It makes no never mind to me. But I do want to show you one more example of an implicit thing. So far I've been using relatively tame, straightforward numbers, like polynomial sort of stuff. I want to do something with some weird numbers so that that's not a horrible shock to your system when that starts to happen in the homework. So before I start this, I want to say that I have written this function down, but I haven't done any of the math on it. So this may, once again, turn into some kind of horrible catastrophe. We're going to see. It's going to be an exciting adventure for everyone. The function I have written down is cosine x minus y minus the sine of x plus y. No, I got that backwards. This one's plus, this one's minus. Minus z equals 0. And the point that I want to talk about is pi over 4, pi over 2, square root of 2. So if we want to verify that this point is in fact on this function, we can plug in pi over 4, pi over 2, and the square root of 2 here to see what happens. And I think we should get here, when we add pi over 2 plus pi over 4, we'll get 3 pi over 4. And the cosine of that is root, oh no, it's negative root 2 over 2. Yeah, see, I've already screwed it up. And when we do the sine x minus y, pi over 4 minus pi over 2 is going to give us negative pi over 4. So this is minus negative root 2 over 2. Yeah, I screwed it up when I said that this should be square root 2. Easy fix. There we go. It's all positive now. So negative root 2 over 2 plus negative root 2 over 2. These two combined will give us negative root 2. Z is just root 2. And that does equal 0. I'm glad I did that check. Probably should have checked it more carefully when I was writing it. I was working kind of fast when I was writing it. So, this checks out. We have ourselves a nice function. And we already have our point, so we just need to get some derivatives and then create our tangent plane out of those slopes. So, first thing we need is derivative with respect to x. With respect to x, the derivative of cosine is negative sine. The inside doesn't change, then we multiply by the derivative of the inside is just 1 here, so that's fine. Plus derivative of sine is cosine. The inside doesn't change. Times derivative of the inside is still 1. It's just going on that x. And there's just some zeros on the back end. So I need to evaluate this at pi over 4, pi over 2, root 2. We get, again, the sum of these things is 3 pi over 4. So the sine of 3 pi over 4 is root 2, positive root 2 over 2. And we make that negative. So we're getting negative root 2 over 2 times 1. When we subtract the two things, we have negative pi over 4. Cosine of negative pi over 4 is positive root 2 over 2 times 1. Oh, so that slope is 0. Okay, that's fine. Derivative with respect to y. Cosine is going to turn into a negative sine. The blob never changes. Multiplied by the derivative of the inside, and that's 1. Sine is going to turn into a cosine. The inside never changes. But this time when I multiply by the derivative of the inside, it's going to be multiplied by negative 1, because that's a minus y on the inside there. And then the derivative of z with respect to y is 0. So I'm going to evaluate this at pi over 4, pi over 2, root 2. And I will get probably the exact same thing I got here, right? So this first piece is negative root 2 over 2. The second piece is also a negative root 2 over 2, because it's the same thing I got here, but negative this time. So in this case, on the y-axis, these things are going to combine to become negative root 2. So this is mx, this is my. We're at 19 minutes already. Gotta go fast. Derivative with respect to z is 1. So when we evaluate it at the stuff, it's still 1, because that's a constant. So the tangent plane is 0 x minus pi over 4 plus negative square root 2 times y minus pi over 2 plus 1 times z minus the square root of 2 equals 0. This is your tangent plane. I will leave you to simplify it if you like. Thanks for sticking around. That's the end of this.